Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to module 3.4. And as you may recall, in the last module, we talked about how we can think about two-dimensional conductors. And one of the concepts I introduced that's very useful and very powerful in this context is that when you have a two-dimensional lattice like this, it is convenient to think of each column as an object. So rather than having little objects connected in a two-dimensional network, it is easier to think of each column as an object represented by, say, alpha, but connected only in one dimension. And that connection is the beta. But the alpha itself now is a matrix whose size depends on how many lattice points we have along the width. And I guess in the last module, what I said is, well, in this particular case, if you wrote down alpha, it would look something like this. And if you wrote down beta, it has a particularly simple form in the sense that it's an identity matrix. And what we could do is, conceptually, you could do a basis transformation, which will diagonalize the alpha. That is, you go to a different basis, one in which this matrix with upper and lower diagonal elements will get transformed into a purely diagonal matrix with different diagonal elements. And because this beta is an identity matrix, it stays the same, which means we can then visualize it as independent wires, each one having a slightly different epsilon, epsilon 1, epsilon 2, epsilon 3, and these are in a way the modes. Now, this method isn't completely general because you see, lots of times you could be doing problems where the beta isn't quite that simple. It's not an identity matrix. What that means is if you try to diagonalize alpha, you might find that beta isn't diagonal anymore. And then, of course, it doesn't help you because then your wires haven't decoupled, you see. So what I'll be doing in this module is telling you about a more general method. The one that where you don't have to do clever things like basis transformation, and it's relatively automatic, you see. And works, as far as I know, in all the examples we have seen, it works very well usually. Okay? So that's what I'll be trying to describe to you. So the general problem then we are talking about is this one-dimensional chain like this. Of course, one-dimensional in the sense that it's basically a two-dimensional conductor, but each column is represented by a matrix alpha. And these alphas are then connected to each other by these beta matrices. Now, question is, so let's say, you have, this is, to the left of this is your actual channel, and what you're trying to figure out is a way to write the sigma that will take into account this entire contact out there. You've got this long infinite contact, and you'd like to write down appropriate sigma so that you can do it. And one way to think about it is that, well, I'm going to use this sigma, you see, to calculate the Green's function, let's say. So we would use it in those first of those transport equations. GR is equal to EI minus H minus sigma inverse. So I'm trying to figure out a sigma such that I could use as my H just this. This is the point in the channel. So for my H, I'll just use alpha and use an appropriate sigma. And the way I define an appropriate sigma is that if I've done it right, then the person who wasn't as clever and handled the entire long thing, he also gets the same answer. See? So supposing someone doesn't use sigmas, but works with the full thing. So then you see his matrix would have looked something like this. His H would look like alpha, alpha, alpha down the diagonal, beta, beta on the upper diagonal, and beta dagger, beta dagger, beta dagger on the lower diagonal. That's what his H would look like. Which means for him, if I were looking at EI minus H, it would look something like this. You see, it is EI means, this is EI, which is like E on the diagonal elements, from which I have to subtract this matrix. So what that means is, at this point, I get something like EI minus alpha, where I is an identity matrix of the same size as alpha. Similarly, here I get EI minus alpha. Here I'll get again same thing, EI minus alpha. And all the upper diagonal and lower diagonals will pick up a minus sign because from this I'm subtracting that. So I'll put a minus sign there. So my point is, so this would be like E minus H for that entire long wire. And if someone took that matrix and inverted it, see, if I just did this, inverted the matrix, then I would get, again, a matrix that would have, many of these. It would be infinitely long like that one. But I am only interested in the first element here, right? Because that is the only point I want to keep in the channel. I really don't want the information elsewhere. Remember, this first thing is this channel part. Rest of it comes from the rest of the wire. So after I invert it, I'm only interested in that element. And let me give that a name, say G, small g. Now the question is, how could I choose my sigma so that if I were doing this just using this as my Hamiltonian, not keeping the rest of it, what could I have? How could I have added a sigma to it so that I'd have got the right answer? Okay? Because after all, when I invert this, I won't get EI minus alpha inverse. I'll get something else. Why? Because of the rest of the matrix. All that's out here. Okay. So now, let me first quickly show you a simple result, which has really nothing to do with quantum mechanics or what we are doing. It's a basic matrix result, see? And sometimes it's called this method of partitioning. Let me explain what that is. This is a basic result. It goes something like this. Suppose I have a matrix A, B, C, and D. So these are all matrices, A, B, C, and D. And I've inverted it, and I get a set of something I could write, say, P, Q, R, and S. Now, suppose I really don't want this full thing. I just want that. I'm just interested in that element, not the rest of it, just that much. See? Then the point is that you could obtain P in the following way. So let me write that result here. And this is not obvious, but I'll show you in a minute. But the way you can get P is by taking A minus B D inverse C and then inverting the whole thing. So if we just did this, instead of inverting this whole thing, if we just took A minus B D inverse C, you'd get the correct answer for P. Now the way you can show this is, well, you see, if this is the inverse of that, what it means is when I multiply the two, if I just multiply those two things, since one is the inverse of the other, I should get identity, identity, 0, 0. In principle, these are not the same identity because this one is the same size as A, that one has the same size as D. But I won't worry about those little things. But now you see I can write out two equations. One is A times P plus B times R is equal to I. And the second equation is C times P plus D times R is equal to 0. Now from this second equation, I can write R is equal to minus D inverse C times P. And if I substitute this back into the first equation, if I take this, put it back here, what I'd get is A minus B D inverse C times P. You see, because I've got AP and then BR becomes minus BD inverse C times P is equal to I. So which tells me that P is equal to the inverse of that quantity. And that's what I wrote here. So that's the basic result I was trying to get at. Okay. So what that means is, let me take this off now. So supposing now, getting back to this original problem, that let us say this is a n by n matrix. This matrix has n here and n here. And this, when I invert it, I'll call that Gn. Okay? So the question is, how can I write Gn? Well, if you, fortunately I just erased it, so let me just remind you. If it is, I've got A, B, C, D, inverse is equal to P, Q, R, and S. And I just want to write P, it's equal to A minus B, D inverse, C inverse. So here, the way I'm thinking is, going back to this is sort of like my A, that's the B, that's the C, and that's the D. See? And so if I'm trying to write Gn, that's kind of trying to write this small p. And so that's equal to that A minus the B, which looks like this minus beta and then zeros. And then D inverse, that's the inverse of that quantity. And then the C, which is this beta dagger. So Gn inverse, as I said, the P is this quantity, which means P inverse is A minus B D inverse C. So this Gn inverse is A minus B D inverse C. That's it. Okay. Now, the important thing is that this beta, though, all these elements are zeros. So when you multiply this times this times this, you'll see that the only thing that matters is the quantity up here, the 1, 1 element of this. Because that everything else gets multiplied by 0, and after you're all done, they don't matter what the rest is. And what is that element? Well, that element is the top element of when I invert this matrix, which is exactly the same as the one I had before, except that previously it was n by n. Now it is like n minus 1 by n minus 1. So I could call this thing like Gn minus 1. So that minus and minus cancel. I have a minus there. I have the beta here. And then the Gn minus 1 beta dagger. So Gn minus 1 is that element of D inverse, that first element, times beta dagger. That's it. So this is the basic equation, basic result that I was trying to get at. So let me just write that here. And let's make sure we understand what it means. So what it's telling me is that if I have a matrix, if I have a n by n thing like this, where each element is this way, and then you have these zeros here, and these are all zeros, then when I invert it, and I'm trying to write this top element here, it will be given by, the inverse of that is given by ei minus alpha, that's this, minus beta times gn minus 1 beta dagger. And gn minus 1 simply means that if I took a matrix that was 1 smaller, not n by n, but n minus 1 by n minus 1, whatever I would have got at this point. And of course, you can realize that when you're talking about an infinite wire and n is long, then gn would become equal to gn minus 1. At that point, it doesn't matter whether you have 1000 or 1001. So this is kind of the equation that you could use to calculate G. So the way this would work is, in practice, something like this, that you'd find your G by, you start from, let's say, G1. Because G1 is easy. G1 means if I just had a 1 by 1 matrix and I invert it, what do I get? Well, I just get ei minus alpha inverse. That's it. So once you have G1, this matrix gives you G2. And once you have G2, that equation gives you G3. And the idea is that starting from G1, you keep iterating, G2, G3, etc., till you get to a point when Gn is not sensibly different from Gn minus 1. That would be it. See? And again, as I said, in this class, I'm not getting into the issues of how you design efficient algorithms. So for example, what I just described to you, there are more efficient ways of doing this. Something called a Sancho-Rubio algorithm, you can look this up. But those are things I won't be going into. But the basic principle then is that yes, you start from that G1, keep iterating, and then you stop when you have a Gn that doesn't change too much. And then you have this G, and once you have the G, the point is that the way you would write down the sigma, remember our original purpose was, here's our channel, this is the contact, how do I write a sigma that takes into account this coupling to the contact? And the answer is, the sigma would simply be, you see, beta Gn beta dagger. So this would basically be beta G beta dagger. And of course Gn, but the idea is that this wire is so long that it doesn't matter whether you take G1000 or G2000, they're all the same. So it's basically beta G beta dagger. That's it. And how do I find the G? Well, I find the G by iterating that equation. In other words, finding a solution such that the G that goes in there will give you the correct answer overall. You see? And one thing that's interesting to check out is, with this approach, you can actually get the simple one-dimensional result also. The one that didn't require all these advanced ideas. You see, the t to the power ika. Because in the one-dimensional example, alphas and betas are all numbers. And so this is just a quadratic equation that you can solve exactly. Now, but the one conceptual point that I want to make before I move on, because this then is the general method that is widely used. That in any problem, once you have alphas and betas, and you want to find the appropriate sigma to connect to the contacts, basically you find the G, which is called the surface Green's function, that's usually the name for the contact, and once you have a G, the sigma is beta G, beta dagger. And the way you find the G is by iterating that. Okay. Now the thing you might wonder though is, and this is a subtle conceptual point that I glossed over, and that is this. I've stressed often that this sigma is non-Hermitian. In the sense, Hamiltonians are usually Hermitian. Because it is Hermitian, the number of electrons is conserved, and that's very important. Otherwise, electrons would be disappearing on you. On the other hand, this sigma actually has a non-Hermitian part. And the non-Hermitian part is responsible for representing the fact that the contact withdraws electrons from the channel. Okay? Now, The question you may ask is, we started with a Hermitian Hamiltonian. Everything was Hermitian. Then how come by doing some matrix algebra, we come out with a non-Hermitian thing? You see, because what we are doing really is taking this and then representing it with an alpha, plus a sigma. And the sigma represents the connection to the contact. So here was something that was perfectly Hermitian. And after we are done, write that a little cleanly, after we are done, we have a non-Hermitian thing. And this is where as I said, I glossed over a small point, an important point actually, a very important conceptual point, and that is that what people usually do is, in this alpha here, they add a small imaginary part, so that what I wrote as EI minus alpha, what I wrote here as EI minus alpha, usually they would add something. Okay, let me write it in red so you see it clearly. Add something which is like I0 plus. And when they write 0 plus, they mean an infinitesimal positive quantity times the identity matrix. So this is what is added there. Now what is the significance of that? Well, usually people justify it mathematically, in the sense that, you see, I mentioned earlier that if these were one by one things, like in a one-dimensional wire, this would be a quadratic equation, and you could solve it exactly. But as you know, quadratic equations have two roots. So it will give you actually two possible results. One would be t to the power ika, and the other would be t to the power minus ika. So in other words, for the Green's function, you'd actually get a retarded one and a advanced one, when you solve that. And by putting a I0 plus, it helps select out the one you really want, the retarded one that actually corresponds to a decaying result, where things are just leaking out into the contact. So that's a mathematical justification for putting it. Physically, the way you can think about it is that by adding a I0 plus, what you're really saying is that in this contact, there is something that kind of withdraws the electrons gently from every point. So at every point, there's a little infinitesimal non-Hermitian part, which causes the electrons to leak out. And that is why when electrons come in from here, they leak out and never get back again into the channel, which is what a perfect contact should do. It should pull the electrons out and not reflect them back into the channel. On the other hand, if you didn't have this 0 plus, then you see it doesn't matter how long it is. Sooner or later, the electrons would reach the end of the chain and again come back. And that wouldn't be what a contact does. And if you did that, the contacts would not perform what they really should be doing. That is introducing irreversibility into this problem. As I've mentioned before, this is where, where these Fermi functions introduce something very different from what you get from a pure mechanics. It's in this non-Hermitian part of it. Okay? Now, so it is as if this little I0 plus withdraws these electrons, and the effect of this long distributed contact can all be included by putting a single sigma here, which is equivalent to all that. But it doesn't matter what you use for that infinitesimal. If you use something really small, then it would take a very long wire before you extract all the electrons. If you take something big, it will take a much shorter wire. And this you'll see in a numerical calculation. As I mentioned, this is actually n minus 1 and this is n. And we stop when the whole thing converges. And the point is, if you use a 0 plus here that is big, it will converge quickly, because all the electrons will have been extracted, and it doesn't matter if it is longer than that. On the other hand, if you use a small 0 plus, then you need to iterate much longer before it converges. But as long as you use something that's relatively small compared to all energy scales of interest. So let's say, KT is, say, 20 millivolts. And if you're using something that is far less than a millivolt, then it really shouldn't affect any physical results that you actually calculate. So this is then the general method for calculating sigma that applies to all kinds of contacts.